Hello everyone. In today's video, we are going to see how to do image compression in Python using fast Fourier transform. So Fourier transform means converting data from a signal domain to the frequency domain. So what we are going to do in this particular coding session is that we'll convert our image, which is in the pixel format, to a to the frequency domain, okay, using numpy.fft2, which will be the discrete Fourier transform in two dimension. Then we will truncate the small values, which will make our image in a compressed format, and then we'll inverse the FFT and we'll reconstruct the image. So let's import our libraries. And I'm importing this image of my daughter, and I'm graying it out by doing an average of each of the pixel over all the three color channels. Okay. So this image is 747 by 537. Now what we will do is for each of the pixels, we are going to do a fast Fourier transform. So we are going to do a FFT2, which is a discrete FFT function in the NumPy library. You also have a SciPy FFT function. You can also use the SciPy one. All right. So once we do the FFT on this two-dimension image, what we get is this array, which is the number, the imaginary part, and the real part of your Fourier transform. So what is Fourier transform? It will convert each of the values in each of these values into the frequency domain. So basically into sine waves, multiple sine waves. Now what we will do is we'll take this entire image FFT and we'll flatten it out. So we are going, and then once it's flattened out, we'll take just the absolute values of it, which is we are going to take the real part of the output here, and then we will sort it in the ascending order. So what we get is a sorted frequency in a big vector. If you look at the length of these, this is about 4 lakh. Okay. And so what we want to do from these sorted frequencies is we want to remove the 90% of these frequencies. Okay. So what we do is 0.90 into the length of this. That will be our index value, and we want to take from this index value onwards, so that this index value, whatever is the value in that, that will be a threshold frequency. So at this particular index, so in this case 361025, you'll take the integer of it, and at this index value from the sorted frequency, whatever frequency value we get, that will be our threshold frequency. So you see that most of these frequencies, so 90% of the frequencies is between 0 to 6467. And if you look at the maximum of the sorted frequency, so the last value of the sorted frequency should be our maximum value. So it is such high value. So in very, so there are high frequencies, but they are in the just the 10% of your data. So what we do is we create a mask which will mask out. So we are creating a low pass filter kind of a thing where we don't want the low frequency values. We just want from our original FFT image, okay, the real part, what we are taking is whatever are the frequencies which are greater than this threshold frequencies, I want only those. So it will, since it is a comparative statement here, this will return to us a Boolean mask. Wherever this value holds true, it will be true, otherwise it will be a false. So once we have this mask, then what we do is we do a brute force multiplication. Instead of brute force multiplication, it's of the same size. So wherever is true is 1 and false is 0. So most of our we expect most of our data points to become zero. If you want to look at the compression ratio of our FFT versus the truncated image, then you can do an NP dot count of the non-zero in the FFT image and the count dot non-zero, count underscore non-zero in the truncated image. Now this is giving us a compression ratio of about 10, and we have removed 90% of the frequency. Okay. So once this is done, now for this truncated image, we will do a reverse inverse FFT of this data, and we will get the image. And we look at the image side by side. So this is the original image and this is the transform image. You will notice you get the image. There is, it's as good as the original image. Not much of this information is lost. Okay. So let's see at which point you will get the information loss. So suppose I want to remove 95% of the data. So my index now becomes 381082 in this case. And the frequency there, so currently the frequency is about 6400. Now the frequency is 11700. And we do this, we take this mask, apply this mask, multiply our image with the mask. The compression ratio has now increased to 20%. We'll do an inverse FFT and check the image. This image still looks quite good. Yes, there is a little bit of data loss here if you look at it carefully. Some of the white areas are seemingly bit less white, and probably here where there is a fur, where there are a lot of edges, there we can see that data is lost. There is some kind of coarseness in the transform image. Now let's look at the 97%. If you remove 97%, that is, you are now removing more and more high frequency data. Okay. So basically you're increasing your threshold. The compression becomes 33%. And now there is some visible problem in the image. Okay. Image, so basically it is looking, so there is a loss of pixel values here. Okay. So, so you see, but most of these low frequency data is not required. So the high frequency data is what is required, and hence you will get a good compressed image without the loss of your original image as a the transformed image. FFTs are used by JPEGs when they are storing the image, and when you view the image, the inverse FFT is done. So this was for the black and white images. You can do this for the colored images as well. In that, you can transform each of the colored channels. So I've written the exact same functions which are written above, but only thing is I've now created a function in which you will take the channel information, you will flatten. So basically you will take the FFT of the each channel, the RGB channels. You will do a discrete Fourier transform. You will flatten out that array, sort it, just take the real values of it, and then how much of it you want to keep or you want to remove, that is what you will write here. That you will take the index position of that, and you will get the threshold frequency. And from that point, so you're comparing your each individual pixel with those threshold frequency, multiplying it and returning the data for that particular channel. And once you will call that particular function for each of your R, G and the B values, and I am hard coding here as a 90%. You can easily pass a variable on how much data you want to keep or how much you want to remove. So this call is for each of the color channels. Once you get these things, then what you do is this transform channels, you will do a np dot d stack of it and convert it back into the final image. We'll take a numpy dot unsigned integer 8 so that you will get values between 0 to 255. So valid values will be there. So when you so I'm taking the original image and calling this function. So if you look at it in the colored image as well, for the 90% of the frequencies which are removed, there is most of the image looks good. There is a slight uh, pixelation part of it, so slight color changes here and at this point. Okay, so these two areas are where there is a color change. Otherwise, most of the image is as good as the original image. So now this particular example here, it is inspired by Steve Brunton. You can plot the pixel intensity as a surface plot, and then if we view this surface, you will I've opened it in a Qt window. So if you view this surface, what you will see is here your image as these sine waves, and if you just kind of adjust it, the sine waves in the view, you see you will then see the formation of the face and the other features. And if you look at it from a different angle, you will see this heat map, right? So this is the darkermost color and this is the light colors. So the way you view this, you will be able to see this different wave and this different intensity. Okay. So I hope this helps you. And yeah, this is how you can do Fourier transform in Python. Thank you for watching.